Welcome. This is a lecture on the measures of dispersions or variation or spread or deviation of the sample and the population. So you're trying to measure the variation of the items in the sum collection, whether it's a sample or a population. So I have, for example, here 5 items in the first sample, 1, 2, 2, 4, 5. That seem to be well dispersed. In the second sample, I have 1, 1, 3, 5, 5. I have like a 2 outlier on one end, 2 outlier on another end, and 3 in the middle. Third sample has mostly everything 1, except one item that is like an outlier. And the fourth sample, I have mostly bigger numbers and one smaller number. They all seem to be dispersed differently. They're not the same type of variation. So how do we determine that? What do we use to determine that? We have a particular measure to do that. The simplest measure that we use for a measure of dispersion is called range. Now range is simply the difference between the smallest and the biggest. So in all 4 samples here, the biggest is 5, the smallest is 1. It will be a range of 4 for all of them. So this is not a very informative measure. It's a measure we use, but it's only going to distinguish between the minimum and maximum, and it's not going to tell you anything what is in between. So the next one that we use is called sample standard deviation. We also use a sample variance, and the difference between these two is that one of them is a square of the other. So we label the sample standard deviation with S, and the sample variance is a square. This is a square of sample standard deviation, and we label that just simply by using a square over S. Lowercase s, sample standard deviation, lowercase s with a square, sample variance. The formula is also in the same relation. The one without a radical is the formula for sample variance. The one with the radical is the formula for sample standard deviation. The idea of this formula is to calculate approximately the average jump away from the mean. So for example, here we have 3, 1, 1, 5, 5. It's obvious that in this second sample the mean will be 3. You can calculate that by adding 1 plus 1 plus 3 plus 5 plus 5. If you do that, you get 15, and 15 divided with 5 is 3. So the 3 is the mean. This one goes 2 away from the mean. This one goes 2 away from the mean. This 5 goes 2 away from the mean. This 5 goes 2 away from the mean. If we don't count 3 because it's not moving anywhere away from itself, we have the average jump is 2. Right? Yeah, 1, 2, 3, 4, going each one of them 2 away from the mean. So the average jump away from the mean would be 2. Okay? The actual average jump away from the mean of the items in the sample is called absolute standard deviation, and we will not use that. But sample standard deviation calculates something similar. So what the formula says you need to do to get to that point? You need to find the mean. So you itemize all of the items in the sample. 1, 2, 2, 4, 5. You add them up. You got 14. When you divide that with 5, you have 5 of them. You get 2.8. That's the mean of the sample. The next step in this formula is to subtract every item from the sample minus the mean. So 1 minus 2.8 is negative 1.8. 2 minus 2.8 is negative 0.8. So again, you are subtracting the item of the sample 2 minus the mean 2.8. The second one, the second 2, or the third item in the sample, again, minus the mean is negative 0.8. 4 minus 2.8 is 1.2. 5 minus 2.8 is 2.2. I will not sum this because the sum would be 0. Something goes above, something below, something is negative, something is positive, they cancel each other. But these are the jumps away from the mean. So it tells you this one is 1.8 below the mean. This one is 0.8 below mean. This one is 0.8 below mean. This one is 1.2 above mean, and this one is 2.2 above mean. Now formula requires also you square all of that. The square is to get rid of the minuses. The alternative would be absolute value, but that is difficult to work with. So if I square all of that, so the first one squared is 3.24. The next one squared is 0.64. You can use your calculator for that purpose, but of course it's very easy to do. 8 times 8 is 64, right? 2 decimals, of course. The next one again, you got 0.64. Square of 12 is 144, so the square of 1.2 is going to be 1.44. And the last one, I think I need to do either some long multiplication or just simply going to use my calculator. My calculator says when you square 2.2, you end up with 4.84. Okay. Now we need the sum of all of that. Why? Because the formula requires that. As you can see, the formula makes the sum. This is a typical thing you do with the average. You make a sum. So you make the mean, you subtract every item from the sample minus the mean, then you square all of that, and finally you add all of that. And that will give you 10.8. You should check that. But the sum of all of those items here is 10.8. This is a symbol for a Greek symbol, uppercase S, for summation. And now I need to divide that with n minus 2, n minus 1. N minus 1 is degrees of the freedom of the sample. That's how it's called, degrees of the freedom of the sample. Now, if the sample has a 5 things, degrees of freedom of that sample will be 4. If the sample has a 50 things in it, degrees of freedom of such a sample will be 49. So you gotta remember that. It's very easy to remember. Degrees of the freedom is a sample statistics. It does not exist for the population. Population has no freedom. There is only one population. But in the sample you have the different things, and that could be depending on what kind of sample you take. So it has degrees of freedom. Degrees of freedom is one less than the size of the population. Now there are theoretical reasons why we make that kind of average. You're gonna have to remember that term though. We're gonna use it down the road. So we have 5 things in it. 1, 2, 3, 4, 5. If we are looking for degrees of freedom, there will be 4. So in my calculation now, I finally have to finish the calculation by, I still did not do the radical. We'll do that in a moment. But we're gonna have to do the 10.8. That's the whole table calculation is just for the numerator. 10.8 divided with the 4. That's gonna be 2.52. You wanna check that out. And then finally you have to take the radical of 2.52. And my calculator says the end result, I think it's 2.52, right? 2.52. My calculator says it's 1.59. I'm not so sure if this is good calculation. Let me see. 10.8 divided with 4. It's not 2.52, it's 2.7. And okay, now I have to take the radical. 0.5. The radical is a power 0.5. You can use your calculator if you have radical on your calculator. Hopefully you do. And the end result of this calculation on my calculator is 1.64 with 2 decimal approximation. There's a lot more digits, but I'm just going to use 2. Okay, this is a sample standard deviation of this sample. This one, we use the first one, not the second one or third one or fourth one. You can check for the second and third and fourth one what that is. So we needed this table for this particular formula. If we only want variance, we will do the square of this number. Or on the way, we already calculated that before we were making a radical, we were making a square root, and I ended up with 2.7. That is simply this 10.8, which is the numerator right here, divided by 4. You can also use this formula for the numerator, which is slightly easier to use. Okay? For this particular formula, that's the same thing. You got this guy, 10.8. The same thing, slightly different. And you only need a 2-column table. You need the x's, 1, 2, 2, 4, 5. You need the x squares. So the square of 1, the square of 2 is 4, the square of 2 is 4, the square of 4 is 16, the square of 5 is 25. Sum of all of them is 50. The sum of x's, of course, we already have 14. So sum of the x squared is 50. So using this formula is slightly easier because you end up with doing the sum of x squares, which is, I just calculated to be 50, sum of the x squares. And then you have to subtract sum of the x's, which is 14. You do have to square that. According to this is a square, so that's 196. You might want to check that out. And divide that with 5. 5 is the n, the size of the sample. You might want to use your calculator for that, and if you use your calculator, it's going to be 50 minus, be careful about the order operation, 14 ought to be squared, and then we need to divide the second term, 14 squared needs to be divided by 5, and once you do that, you got 10.8, just like moments ago. So this is alternative formula to use, this one here, for which you only need this table. Much easier than this one. A lot less writing and less calculation. You don't need any subtraction. Okay, so this formula. And then you take a radical, of course, the radical, well, the numerator, of course, had to be divided with 4, and then you take a radical. So that's how we get the formula 1.2, by using this replacement instead of this previous numerator. So in this formula, we have numerator this way, which is equal to this. So you can replace it here, so you can use the formula 1.2. Or you can use the formula 1.3. Now the formula 1.3, the sample standard deviation in this formula, is achieved by simply multiplying up and down with n. And this is basically the same as 1.2, but slightly prettier. Should we say, looks simpler, because this one has double fraction, fraction within a fraction. This one doesn't have anything like that. So how is this formula used? Very simply, by using this 2-column table, when you just need the x's and the x squares. So the formula says, okay, you need to get a radical for sample standard deviation. You need to have n time the sum of x squares. The n in this case is 5. You have 5 items. Time the sum of x squared is 50. So this is the sum of x squares time n, 50, minus sum of x's, which is 14, ought to be squared. So subtracting 14 squared. And then you divide that with n, 5, time degrees of freedom, n minus 1, 4. So n multiplied with n minus 1. Okay. And this is going to lead to exactly the same standard deviation. You don't want to check it out. We're just going to be checking that out, so that we already know the top is 5 times 50, 250 minus 196. So that's 54. Okay? So again, you should check that out. 250, 5 times 50 minus 196. So that's 54. Divided with, down there we have 20. So 54 divided with 20 is, we already had that before, 2.7. So that's the variance. Without square root, it's just a variance. Now once you do the radical, you will get an approximation. There's lots more digits than 2 decimals. So I'm going to use approximation, and you end up with 1.64. I would say this is the easiest formula to use. And again, the idea of sample standard deviation in either one of those formulas is to get the approximately average jump away from the mean. So this is the table needed. You can practice yourself for calculating sample standard deviation, either one of those, the next 3 samples, and you see how that works out for you. We're gonna do some more realistic examples down the road. I want to point out that if you are going to calculate the population standard deviation, now when you don't say sample standard deviation, you mean population standard deviation. So the population standard deviation is a parameter, meaning there's only one population. And that is calculated differently. The only difference in terms of a formula is labeling S for the sample standard deviation, Greek S, sigma, for population standard deviation. So Greek symbol for population. The mu, M, mean, is the symbol we use for population. The mean of the population is labeled with a Greek symbol M, Greek M, mu. Now when we do that in this formula, we just simply use x bar. Everything else is the same. So you have the summation x minus x bar minus the mean squared, down there divided with n minus 1 and radical. There is this difference also about dividing. This one doesn't have n minus 1. Uppercase N means the size of the population. But it's not n minus 1. The population doesn't have degrees of freedom. So we are averaging just with the size of the population. So let me point this out, the difference, and up closer. So when you're calculating the sample standard deviation for the sample, you are using the following formula. So different label, sigma S, S for the sample, sigma for population. The summation stands in both formula, radical stands in both formula. You also have an items in the sample or the population. The same way, you're subtracting from the mean. Again, the mean is calculated the same way, just arithmetic average. That ought to be all squared. That's the same in both formulas. And at the end is divided with n minus 1 in case of a sample. In case of a population, it's divided with n. Also, there is a different label. Population has the uppercase n for the size of the population. Sample has the lowercase n. All right? This part, the numerator, is the same in both formulas. You can see the only difference is labeling. Mean of the sample is labeled x bar, mean of the population is labeled mu, m, Greek m. So 10.8 would be, again, if I use the same formula for that same sample, I'll get 10.8. If that is a population, I would calculate population standard deviation. Then divided with 8, as opposed to divided with 4 I had before. So before I was dividing with 4. Here, radical 10.8 divided with 4. This time, 10.8 divided with 5 radical. Now that's a population. And then you get, if you divide 10.8 with 5, you get 2.16. And the population standard deviation turns out to be 1.50 as opposed to 1.64 sample standard deviation. Population standard deviation is always going to be smaller than sample standard deviation for the same set of data. You have to know whether you have a sample or a population, so you would know which formula to use. So it's not that the same sample has a population and sample standard deviation. No, it has only sample standard deviation because it's a sample. Population has only population standard deviation because it's a population. It's calculated differently. You have to be aware of that. Okay. It also has a helpful formula. So, for example, here, this is the formula for the variance that is easier to use. That also uses sum of x squares and sum of x's. So you get sum of x squares, which we already know was 50, right? Divided with 5, and then you have sum of x's, which is 14 divided with 5. That's actually mean. This is just the mean, the average. So you have here 50 divided with 5, which is 10, minus 2.8. That was the mean. It ought to be squared though. So you got 10 minus 2.8 squared, like here. And of course you're going to take the radical at the end. And you end up with 1.50 again. So this is an easier formula to use, this one, than this one. Again, because you're going to use just the x's and the x squares. And again, like before, the variance means the square of standard deviation. One set of data will be either a sample or a population. And if you use a sample, you will calculate sample standard deviation. If you use a population, you calculate population standard deviation. The square of either will be variance of the sample or of the population. We also have coefficient of variation. Why is that important? Okay, here's the story. I got something calculated here that is from something else. The story is that the variability also depends on what size you're talking about. For example, if I'm to purchase the coffee cup, just a 1 cup of coffee. In one place I could get it for $1, another place for $2, another place for $3. What would I choose? I guess I would choose $1 if it's the same taste. I hope it's not any difference in terms of how good the coffee is. I would choose $1. Why pay $3 if I can pay $1? This sample 1, 2, 3. So this is the sample of only 3 things. 1, 2, 3 has a sample standard deviation of 1. Now you can easily calculate that by using the formula 1, 2, 1, 1 or 1, 3 that we had before. Or you can just think about it. I mean, we have here obvious mean is 2. 1, 2, and 3. When you sum it up, it's 6 divided by 3. You got 2. The mean is 2. This one goes 1 away from the mean. This one goes 1 away from the mean. The mean moves nowhere. So the average jump away from the mean would be 1. And that's what standard deviation is. It is 1. Okay? But the coefficient of variation, it's not just a sample standard deviation, it's a sample standard deviation divided by mean. The relative size of the numbers is important. So when you divide the sample standard deviation 1 with the mean, which is 2, you end up with 1/2, which is 50%. So this stands up for coefficient of variation, which of course you're going to have to divide with 100% to get percentage. So you have 50% coefficient of variation in this sample. Now in this particular sample, that's the first sample of coffee cup, a cup of coffee price. The second sample, let's say I want somebody to do a small removal from my driveway. One person is asking me $101, another $102, and the third one $103. I guess I would go for the one that is the most convenient, somebody that can do that fast and quick and it's close, rather than saving $1 and then having a issue down the road, right? So I'm mostly concerned about it. I'm not concerned about the difference between these numbers. It's pretty much the same in terms of how big the numbers are. However, the sample standard deviation of these 3 numbers is also 1. Again, you can use either one of those formulas that we have and you will find it out that it is 1. Now when you divide 1 with the mean here, the mean of these 3 numbers is 102. You can check that out. So 101 plus 102 plus 103 is 306, divided with 3 is 102. 102 is the mean. So if you divide the sample standard deviation 1 with the mean, which is 102, you get 1%. Actually less than 1%. That's a coefficient of variation. So coefficient of variation, you divide the sample standard deviation with the mean. You also multiply with 100 to get percentage, right? Or you can just simply read as a percentage. So this sample is a 50 times less variation than this sample. The coefficient of variation is 1% versus 50%. Okay, coefficient of variation is comparative measure. You can compare 2 different samples. They have nothing in common in terms of units. The coefficient of variation will not just take in account how far away the numbers are from the mean, but it will also take in account how big the numbers are, which is also important for understanding the variation. Okay, let me calculate something realistic. This first example is about the profit per employee in thousands of dollars of computer companies. The first company has 29,000 profit per employee. What's a profit per employee? That means the company has a revenue, you subtract all of the possible costs, the benefits you pay, and anything else, and then you end up with a pure profit. Divided with the number of people you're employing annually, and you get a profit per employee. How much you're making per employee. How much is the employee worth to you? The first company has 29,000, the second 24,500, the third one 31,000, and on you go the last one 19,100. They're all doing well. Okay, if you subtract the biggest number 31,000 and 19,100, this is in $1,000, so you can just say 19.1, right? The unit is thousands. The unit is thousands of dollars. So when you subtract the minimum and maximum, you get $11,900. That's the range of the sample. Now, if we want to calculate the sample standard deviation, then we're going to use the formula. I'm going to use 1.3 formula. First of all, I need to itemize everything. I need to itemize the excess. So this 29.0, just basically copying these numbers in the table. The square of all of them, so 29 squared is 841. 24.5 squared is 600.25, and on you go. Sum all of the x's, you got 182.9. Sum all of the x squares, you got 4,897.63. And if we use the formula 1.3, the formula 1.3 is right here. That's the sample standard deviation. What do we need to do? Radical, and how many things we have? 7. I actually have an extra column just to itemize them, but you don't need that. It's visible that there are 7 of them. So this is 7. Wrong number put in here, right? And so it's here, and it's 7. And then minus 1 is 6. In the file on the Blackboard, this is correct, but here I have 7 and 6. Okay. So then you have sum of the x squared. Sum of the x squared is 4,897.63. That's what I have here. So I just have to multiply n with the sum of x squares, which is right here. X squares, the sum on the bottom. And then minus, I have a sum of x's, which is 182.9 right here. That will be squared. Then you're going to subtract that. You can check it out. The formula, what would that lead to? Let's see. So we have 7 times 4,897.63 minus, so this is just numerator, 182.9, which needs to be squared, and I get the numerator of 831. Interesting. I didn't get any decimal. That's amazing. Now that is divided with 42. Down there is very easy. I don't need a calculator for that, right? It's 7 times 6. That's divided with 42. Now I get lots of decimals, and I take the radical out of that. The radical is with a power of 0.5, or if you like, you can use the radical symbol in your calculator, whichever calculator you have. And I got 4.4481135565. Let's just round this to 4.45. And this is sample standard deviation of the sample. Now I already said before I was taking radical, I got 19.78, you can say 19.79. To decimal approximation, that will be the variance. The coefficient of variation, of course, is dividing the sample standard deviation with the mean. But the mean is okay. I get sum of all of them is 182.9 divided with 7. I get a mean $26,130. Now, if you divide these two, sample standard deviation is also in thousands of dollars. The variance is in the square of thousands of dollars. So you divide these two, the end result is going to be 0.17, and now we are reading this with in terms of percentage, or multiply with 100 and use unit of percent. So that's 17%. This number here is 17%. Coefficient of variation of the sample is 17%. We would say this is not really a large variation. I think the cutoff for a bigger variation would be somewhere like a 20% to 25%. Coefficient of variation should be like that. Okay? Let's go one more. Percentage of Canada goose nests that are successful. That would mean that out of the nest, there is only one gosling, only one. There is at least one gosling surviving. So you get something out of the nest. That's successful. So Canada goose nests in the North America and Canada and northern part of the United States. And then they travel during the winter season to the south. But they nest in the north. So in this region, we have 23.9% of the nests successful, really bad. Less than 1 out of 4 nests actually have something. That means they're probably disturbed in that area. In the next region, they have 52.5%, and then 60%, 68.5%, and so on. The best success was one region when they have 78.6% success, and the worst one is this one when they have only 17.8% success. So just looking at those numbers, it would tell you immediately there's a big variation here, and we will discover that by calculating parameters, so statistics of deviation. So we want to calculate the range. The range is easy to find out. The difference of maximum minimum is 60.8%. Okay, now I want to calculate sample standard deviation out of the sample, so I itemize everything here. Nine things. You got 9 things here. 23.9, 52.5, and on you go up to the 52. Sum it all up because I need to calculate the mean. I get 483.3. To calculate the mean, the average success of the nests in this sample of 9 is 53.7% success. Okay, so now I'm going to use 1 point. You can check this. I'm using here 1.1 formula, but you can check 1.3 formula I'm going to use here. And in 1.3 formula, we have, this is the formula, right? So we're just copying the formula 1.3. And inside I need to put n, which is 9, times the sum of x squares. And the sum of x squares here, those are the x squares. It's just the square of the guys in this column. The sum of x squared is 29,340.51. That's right here in the formula. So I'm replacing that. The next one, I need to have a square of the sum of x's. The sum of x is 483.3. You square that. And now you need to multiply this. The first term is also multiplied with 9 minus the square of 483.3. Use your calculator. And then finally, you need to divide it with 72. Why? Because down there we have n, the side of the sample, multiply with n minus 1, the degrees of freedom. So you have n times 8, which is 72. All of that, you need one division after you're done with the numerator and denominator, then radical, we end up with 20.58. 20.58 is the standard deviation. Okay, the coefficient of variation is 20.58, standard deviation divided with the average success, 53.7. We're talking about percentages, right? Average jump away from the mean is 20.58%. The average of all of the successes of the nests is 53.7%. When you divide these two numbers, you get 38.38 or 38%. Now, when you compare these two examples we calculated, the variation of profit per employee in the 7 computer company sample was 17%, While we were getting that for the Canada geese, we get 38%, more than double. And so that confirms what we already saw. Those numbers are not too hard to discern because the samples are small. The variation is significantly higher in the success of nesting of Canada goose than in the profit per employee in the computer company. So we can compare two completely, totally unrelated samples, right? The profit per employee of computer companies has nothing to do with the success of nesting or Canada goose, but you can compare them using coefficient of variation. Just by using the sample standard deviation, that will not be possible. Again, the sample standard deviation I calculated here shortly was by using a 1.3 formula, but you can use 1.1. I actually did that here, 1.1 or 1.2 formula, so you can check this out. These are the formulas for the sample standard deviation. One of those three. The one, the theoretical in the very beginning, which explains what it is, what we are doing. We are calculating the average jump away from the mean. This formula. And that formula, of course, calculation requires 3-column table, or you can use the shortcut that you just need to calculate the numerator, but the rest is easy. The numerator by using this helpful formula, so that gives you the second formula. Doesn't look attractive, but calculation is easier than the first formula, requires only 2-column table, or you can use this 1.3 formula, which is basically 1.2 formula without having double fractions. You have only single fraction under the radical. Remember, the variance is the square of the standard deviation. And remember another thing, that the standard deviation of the population is calculated differently than the one from the sample. So this is all about sample here. And this is what we will usually calculate, sample standard deviation. But if you need a population standard deviation, you're just going to use a different one. Okay, I'm going to have to show you also how would you use calculator for that. Well, if you use a calculator, you need the bottom statistic in which you're going to put the data. I put the data in the column 2. So I get 1, 2, 2, 4, 5. The same sample in the beginning I used, not the Canada goose, not the profit per employee company, but that sample I have in the beginning. 1, 2, 2, 4, 5. I itemized that in the list 2, notice. And then you go for the statistics and calculate option. Option calculate. One variable statistics. Select that. And list, you have to put up the list you have the data in. The data I have is in the list 2. And then just simply calculate. And you got everything you need. So the x bar, the mean of the sample is 2.8. The sum of all x's is 14. We actually have that calculated by using this table, 14, the sum of all x's. The sum of x squared is 50. The sum of x squares in our table is also 50, of course. And then we had the sample standard deviation, 1.64, 3167673. That's about as much as I calculated here by using formula. And then it's a population standard deviation. So this is S of x's, right? Uses a label for the variable. The sigma of x's is 1.46969 and on. And I also rounded that to 1.50. So this is our calculation, the same. The tells you the number of things in the sample is 5. And on you go. By the way, you can say, okay, this is both sample standard deviation and population standard deviation. Which one am I going to use? Well, your calculator doesn't know, because you just give the list of the data to your calculator. The calculator doesn't know whether it's a population sample standard deviation, sample standard deviation, or population standard deviation. So it gives you both. You decide. What did you have? You need to know, is it population or a sample? If it's a sample, then you use the first one. If it's a population, the second one. Again, population standard deviation of the same set of data is always going to be smaller than the sample standard deviation, because we are dividing with a bigger number, with n, as opposed to degrees of freedom, which is n minus 1. So you should notice that. So you need to know, before you start calculating, what is the data. Is the data from sample or from population? Now, if it's a population, it's a different formula. Okay? So that's my story about the measures of dispersion. So we introduce a range. We already knew that from before. sample standard deviation, sample variance, which is the square of the sample standard deviation. I also talk about the coefficient of variation of the sample. And then we also have the similar things for the population. Population standard deviation, population variance, and the coefficient of variation of the population. Of course, population also has a range. Okay? I hope this is easy for you. You should definitely practice the homework. So I'll see you next time. 40